this work is entitled Modeling Sparsity, Heterogeneity, Reciprocity, and Community Structure in Temporal Interaction Data, which in other words, just to make it a bit more understandable, is how we use Bayesian nonparametric tools and point processes to model these temporal interactions. And of course, I will explain much more later on. So my plan is the following. I'll start by giving some motivation for this work and what is the context and the main question we're interested in. So why do we care? And then secondly, I'll move into this, how I call local interaction property, which is the main property of interaction I look at. And I call it local because in the simplest case, it's just, two atoms, two people interacting. Third, I'll explain this global ecosystem where I embed my, my nodes, my people here, because there is interaction between two people, but they belong to a bigger network. And lastly, I'll explain how we do inference and how this model performs in some data sets from social settings, and also how this performs in comparison to some alternative models in literature. So firstly, why do we care? So my goal here is to model temporal interaction data in the form of triplets, which come in the form of I, J, T. What does this mean? So a data point for me is this triplet I, J, T, which means that there is an action from I towards J at time T. So we have information on the direction and on the timestamp of this interaction. And the natural question that arises here is why does this happen? Why do we observe this interaction? What are the factors that underpin these interactions? And here in this simple case, in a single data point, is just two people and a timestamp, but we assume that everything belongs in a bigger network. So I and J belong to some network. So apart from the local properties, what are the global properties that are observed in this underlying network? I focus more on social networks, meaning messages being exchanged between people, or online platforms where you can post something and then somebody else responds, and then there's this series of events. But of course, these sorts of interactions appear in other contexts, like biological data. We have protein interactions or neurons like firing against each other, and where we observe excitation and inhibition activity. In all these scenarios, the goal is similar. We want to uncover the trends, so understand why and how this behaves, or how often we observe these interactions, for instance. And once we do that, we understand what is the model, what this is, then how can we use it to predict future links? So if I'm the owner of this platform of online posts, kind of predict the activity in the future, because this will help me in my future decision making and knowing how how much activity I'm expecting. And if I'm interested in some sort of intervention effect context, I can use my knowledge in order to measure that effect I'm interested in. Let me start with a simple example. So simplest case, just two people. So I will keep saying people because let's focus on this social scenario, like social example of two people exchanging messages. So let's say we have here A and B, two people, and these are the relative time points of their messages being sent between each other. So how does this appear? We assume that we know the history of this. So firstly was this B person in my data set, and then he sent an email to A at 2.A, relative point, time point 2.A, and then another one, and then A responded. And then B sent another one, and then A responded again. And then we have another message from A to B at time 7.8, and then the final one at this point. So this is like a toy example of how messages between two people could have arise in this fixed time window from 0 to 10, say. Oh, sorry, there was another 8.4. Yes. Okay, so we observed that nice and clear, two people exchanging messages at different time points, but what is really the property I'm interested in? So the property I try to show with that example is what we call reciprocity or reciprocation, which means that an action from A to B increases the chances of the similar action being returned from the other side. So A sent a message to B, therefore B replied. This is what I'm saying. And it seems trivial, but I like this example because it's easy to explain. How do we model this reciprocity? So A having an action towards B and B responding. What is the main tool I'm using here is inhomogeneous point processes, namely Hawk's processes. So in the simplest scenario where we have just one Hawk's process, to understand this Hawk's process, I usually focus on these two ingredients. So we have this capital N of T, which is the counting process. And if I have one process only, I will have N of T counting the number of events from 0 to T. And this is a step function that increases in time. But what is the really important component? What is the rate of events occurring? This is explained and expressed by lambda of T, which is the conditional intensity for another event occurring in time T. So when we say that N of T is is the realization of this Hawk's process with conditional intensity lambda of T, what we're really saying is that lambda of T is the rate. So the probability of another event occurring in this infinitesimal time interval T and T plus dt, conditional on the history, like very important that we have here the history, is equal to lambda of T dt. So that's how a single univariate Hawk's process works here. But what am I interested in? I'm interested in two processes because I have a process from A towards B and I have a process from B towards A because the direction of an action is important here, like who sends the message is important. So since I have two directions and two processes of messages, I need two Hawk's processes. Essentially one like bivariate one, but you should think of it like two. So we have capital N of AB explaining the events from A to B, and then capital NBA explaining the events from B to A. And these two have corresponding intensities, lambda AB and lambda BA. So what am I saying is that this capital N now of AB, it counts the events from A to B up to time T. And similarly from B to A. But how do I really encode this reciprocation? How do I encode that an event from you increase the chances that I send you one in the near future? I have to do it. I have to encode this behavior inside the conditional intensity, because the conditional intensity is the ingredient that will determine when an event occurs. So the rate of events from A to B, in other words, lambda AB, takes this form, which is some constant, and then plus this kernel that we can kind of ignore it for now. But the important thing is that this is integrated against the counting process, so the measure of the opposite side. So all the events from B to A. This is saying that the probability that I'm going to send you another event now depends on whether you sent me one in the past. And similarly, for the other side, again, the rate of events from B to A depends on whether A sends messages to B in the past. So this is the framework of mutually exciting Hawk's processes. One process excites the other. Events from one process encourage events from the other side. And I will explain later on, what form we take for G, and if we want them to be the same or not, and what are the implications for the mod. So if I go back to this example, I think it's always nice to show things graphically. So you should be looking at this diagonally. So you remember, when we go back, we have A and B. A sent these messages, B sent these messages. How do the counting process and conditional intensity process look like graphically. So top left, we have the counting process from A to B, which means every event that is being sent from A to B here makes this process go up by 1. It just counts the events. So the first one was at time 5 point something, so it goes up by 1. Then the second one was somewhere here, so it goes up, and so on and so forth. What is the interesting thing? It is that the interesting thing is that, okay, A sends to B a message at like 5 point something, and what is the impact? The impact is observed in this graph. So the impact is that the intensity of the opposite process instantaneously has this this increase, this jump here, because since A sent this message to B, then the rate of events, the probability of B responding is high. And then it here it goes down, and then in this other message from A to B, similarly, again, the probability of response is pretty high from the other side, and then it goes down. Now, here you can see that this decay that I have here, like between consecutive events, it's really fast. It has this exponential decay because the form of that G function here, the kernel I have here, I've taken it to be exponential for this example. So this is saying that if you don't reply now, the probability of responding to me like dies out really quickly. And for the other side, the other diagonal, the same story occurs. So we have this first message from B to A, and then the effect is that A is likelihood of responding, the probability of responding is very high, and then it goes down exponentially fast. So that's how a pair works. That's how what's the model and the assumptions we have on the interactions between a pair of people. But we're interested in networks. So we know that these two people belong in a network. So in this very simple toy example I have here, this is the big network of people. We had A and B. This is what I've been focusing on, but we also have person C and D and E, and there are interactions between all these pairs. So how do I model a network? I just take the same idea. So before I had A, B, now I'm saying that for every directed pair I have, IJ, I will associate a process on that. So Nij will be the counting process for the events from I to J. And this Nij will be mutually exciting with Nji, which is exactly the opposite process. So same story as before. The only thing that I changed here is that this new ij and new ji, in theory could be different, but we are taking it to be the same because actually that mu ij equal to mu ji equal to some nu is proportional to the probability that these two people are connected in the first place. This is a network, so we also have connection probabilities, and we are saying that once you are connected with somebody, you can start having this excitation behavior. So in this kind of Facebook type examples I have of messages between people, you have to be friends with somebody in this platform in order to start exchanging messages. And this is the same because the probability that I am connected to you is the same as the probability that you're connected to me. But then same story. And for the graphical example I showed before that had this exponential decay in the kernel. So if you don't reply to my message, you probably never reply. It's because we had this form. So for these examples I have here, I assume that there is an exponential kernel in the excitation part. And it's taken to be the same here. You see this like eta and delta parameters are the same, but they don't have to be. In the examples I looked at, there was this kind of similar behavior between people. So like everybody took the same time on average to reply. So it made sense to have it the same. Now I explained how this works in a directed graph, but of course, if I forget about the time and the direction, I am left with this global like network structure, this as a simple graph, so with no direction, no time, just a picture of the network in time, like a picture of who is friend with whom at this point in time. And I'm interested, so apart from all the excitation I explained, I'm also interested in the properties that we can observe in such network structures. And how do we model that? It's through that base intensity mu ij. I explained very briefly before that mu ij, which is the base, the background intensity for my Hawkes process, has to do with whether two people are connected. And those base intensity through their parameterization that we take to be based on vectors of completely random measures, their parameterization prescribes a series of properties that we're interested in. So the first one is what we called assortative mixing. So we have two nodes, two people, and we assume that the more similar they are, the more likely that they're connected in the first place. And the way this is incorporated into this model is that everybody, like every node, is represented by some latent vector, and we take this this link probability to be proportional to a dot product. So the more similar the two latent vectors of two people are, the more likely it is that they're connected. And I will explain this in the next slide. But we care about assortativity. The second one, very important one, is parallel degree distributions. We are interested in modeling these interactions in graphs where we are able to have a parallel graph. So the degree distribution is a degree of a node is the number of edges attached to a node when we talk about simple graphs. So not counting all the edges that would be induced by messages. So, but when we take a simple graph, the degree of a node is the number of edges that's attached to it. And in many interesting applications, this degree distribution is parallel. And we want to be able to capture that in the model. In other words, we want to be able to capture a degree distribution that says that some nodes, some people have a huge number of interactions, but at the same time, most of them have very, very few, like just one. In the social settings, it's these influencers I have here with like a ton of connections, and then like the rest of the world with like very, very few. Now, very closely connected to parallel, we have sparsity. Sparsity is an asymptotic property, and what it says is that we want asymptotically the growth of the number of edges to be sub-quadratic than the number of nodes. So this is how we define sparsity in graphs, and the opposite, like if a graph is not sparse and it's dense, it means that the number of edges grows quadratically with the number of the number of edges grows quadratically with the number of nodes. And more simply, like we're interested in a sparse graph, which means that only a small fraction of all the possible pairs are connected. And finally, something that I'll not talk too much in this talk is that we are also interested in having some probabilistic symmetry, in the sense that we want the distribution of the graph to be invariant to the permutation of the nodes. We care about all these exchangeability assumptions that usually come based on nonparametric models. So all of this is just to motivate the form of the background intensity mu ij that I take in this model. And what is this form? So mu ij is being shown here in this equation 7. So we have for every node in the graph, or every person in the graph, there is an associated latent vector. So these vectors of size p are draws or realizations of vectors of completely random measures, and is of size p here, where p is fixed, because we assume that in this graph, in this network of people, there are p latent communities. So there is this fixed number of latent communities, like groups, like overlapping clusters, and people have affiliation to these communities. Therefore, the like WIK, which is the kth entry of the ith person here, shows how much affiliated that person is to that community. So in order to model this assortative mixing I explained before, we need to have something like a dot product for connecting these two people, because then the more similar their affiliations are, the more, like, the higher this dot product will be, and then the more likely that they are connected. So the vector, the form of this vector of completely random measures that we choose for our network is by the work of Griffin and Laysen, essentially called compound completely random measures, which we have used also in some like previous work of ours, where there is no time, it's just static graphs with this community structure. So when we observe, how do we observe these latent vectors? So this WI, so I being, you know, a person here, and P being the number of latent communities, these are just, you know, realizations from this vector of completely random measures, which we take to be a compound completely random measure because of the nice properties and tractability they have. And they take a quite nice form. I'm not going to take like too much time on these details on the CRMs, but I want to point out that, you know, all this sounds a bit, you know, like a bit exotic, but the form that these the realizations of the completely random measures take is very easy. So it's being modeled as a product of an IID vector here of gamma random variables. So like nothing hard up to here, and then times this WI0, which are points from a completely random measure with some like mean measure rho 0. So the interesting thing that would bring all the nice properties on sparsity and everything is that this WI0 parameter, univariate one, that is inside the vector of every single person, these are draws from a completely random measure. So these are points, these are positive, this is a weighted sum of atoms where their weights are WI zeros, and by the form of the completely random measures that we take, we can capture this series of properties. In our case, we care about the generalized gamma process, which corresponds to this case of a measure of a mean measure rho 0. And why we care about this? Because it's only tuned by essentially two parameters, the sigma and tau, and we have some very nice analogies with the properties. Essentially, if we take the sigma to be negative, we end up with dense graphs. If we take the sigma to be non-negative, we end up with sparse graphs, and then tau just nicely tunes the shape of the exponential cutoff of the degree distribution. So happy to come back with in this like a CRM construction. I guess what you know I would like you to take out of here is that, you know, we take this like complicated building block of a vector of completely random measures, but at the end of the day we have very interpretable hyperparameters. So those the IID vector of betas, which is a gamma distributed, directly tunes how much affiliated everybody is to a latent community. Then we have sigma that directly tunes the sparsity and the degree heterogeneity, and tau that also connects to the degree distribution. And then from before, if we take the exponential kernel with eta and delta, that will directly tune the reciprocation. So in the end of the day, we have this like four or five parameters to estimate and understand and interpret. So this brings me to what happens in inference time. So suppose we observe, we have observed a set of some individuals over a period of time t, and for each of them we have this IJT information. So all the actions like messages sent or anything from I to j at time t. So this directed temporal interaction set. we're interested, so we're Bayesians always, we're interested to estimate the posterior distribution on the parameters given the data. Now, I have distinguished the parameter set in two subsets, this that I called phi and xi. So in order to differentiate between the parameters that tune the kernel and those that tune the graph and the power law and sigma and tau and all of that stuff. So phi denotes the kernel parameters, so eta and delta, essentially whatever has to do with the excitation and the reciprocation, whereas xi is the base parameter, so the background intensity. So there are these two kind of sources of parameters I'm interested in, phi and xi. The reason I'm introducing like these two distinct sets is because we estimate them in a like two-stage procedure. The reason we do that is mainly like for computational, flexibility, because it was quite, involved and expensive computationally to have, a full kind of, let's say if like I give something with like updating each of these parameters iteratively. But it turned out that taking this approximate two-stage procedure, firstly, gave like a very quite like fast inference procedure, and also when empirically we performed an empirical consistency study, we saw that the posterior would concentrate around the true values very nicely. So the idea is that we first estimate the structural parameters of the graph, so the static ones, whatever that has to do with the degree distribution, the sparsity and everything, and then conditioning on a point estimate of those, we estimate the rest. So it's like when we have this Hawkes process intensity, we first estimate the background intensity, which then connects to all these structural parameters of the graph. And then we estimate the kernel parameters, conditioning on a point estimate of the background intensity. This is what this slide wants to say. Now, how do we do this in these two stages? So the first one, the structural parameters, these are, all these like vectors, the vectors of completely random measures I mentioned, and the mu ij's. This is the first stage, and we know how to do it because this is our previous work on overlapping communities in graphs. And a lot of time was spent there as well on the efficiency of the MCMC scheme, and the sampling we have there based on Hamiltonian Monte Carlo would ensure that the inference is linear per edge and per node, which was pretty cool. So then we use that. We estimate the structural parameters, and then this can give us the background intensity. And at the second stage, we would estimate these Hawkes kernel parameters, eta and delta. And this was just, by Gibbs sampler with a Metropolis Hastings step for each of these two. And the idea, let's say the inspiration for this two-stage inference came from the paper of Jacob et al., where they motivate modular Bayesian inference. So overall, what does this model learn and how does it perform? Just to sum up things a bit, I care about learning the global graph structure, which means community detection, because we can uncover how much affiliation each person has to the latent communities, and we can uncover blocks in the graph structure. We learn the degree distribution, so we can see and detect if there is a rich get richer phenomenon, which there is. And then after being done with this graph structure, we go to the reciprocation effects. Okay, we observed this excitation between people. How strong is it? So if you send me a message, how likely I am to to respond back to you? And of course, you could argue here that it depends on who sends it and what time, all of these things, but here we kept a more kind of uniform approach. So how strong is on average, the impact on actions between people, and how fast does it decay? And the philosophy of our Bayesian inference was this modular two-stage approach. The ingredient that made the graph inference very fast was this Hamiltonian Monte Carlo step. And how do I use this? I use this framework and inference in a series of data sets in order to uncover this community detection and degree distribution, and then predict the number of future links for every pair in my data set. So when it comes on messages, how many messages is every single pair expected to exchange in the next kind of 10 days or 10 weeks or anything you're interested in. And then of course we compared it to alternative models, and it showed like really good, actually, yeah, superior performance. So if I have the time, I'll spend a bit of, a little bit on some graphs here from these experiments. So this slide here concerns only the structural parameters. So understanding the graph behind. The first row is to show that we are able to do some sort of community detection. So for every person, this vector of affiliations is being estimated. And then each person is assigned to a cluster, although people are allowed to have multiple affiliations. Here I assign them to their biggest one in order to induce some sort of clustering and show that we get this high intensity and less intensity blocks that corresponds to some ground truth data we have on what are the communities in these cases. So the intensity is proportional to the number of links. So in the first one, the data set has some ground truth information that there are 4 blocks for communities. The second one had 2, and the other 2 here had 3 communities. So by assigning everybody to their cluster, we see that we recovered somehow this community behavior. The second row is aiming to show the degree heterogeneity. So apart from assigning people to their highest cluster, so their their biggest affiliation, we also order them. We order them from rich to poor in the sense of who has the most connections to the person that had the least connections. So we observe that this degree heterogeneity, so the coexistence of people with huge and very few connections, and this exists in every single block. Just to bring a bit more context to this, if we were to use a model that that could not handle degree heterogeneity in parallel, what this would do, it would cluster the people and split the people in the rich and the poor. So in those that have very few connections and those that have a lot of connections. But having a model here that can account for this degree heterogeneity, like truly, we uncover this heterogeneity within each cluster. And finally, the last one is just the degree distribution in log scale, where the red dot is the actual data, the empirical one, and then this blue one is a 95% credible interval to show that it captures quite well the data. And here, although this is not like super meaningful, it's just me splitting the data sets in train and test, and from the train data set, estimating all these parameters, eta, delta, news, everything, and then using that to predict the number of links between the number of messages between every single pair of people in the future, and then summing that up and comparing to the ground truth. So this is just, the root mean square error between the true and the predicted number of links for different data sets and for different models, aiming to show that it has the smaller error in all these cases. And maybe this is expected because, the properties here we're interested in are captured by this model, whereas in all of the other cases, some property is missing out. So overall, why this is a nice model. If I put, my scholar hat on, I really like it because it, it generalizes existing models that deal with reciprocating relationships to the case that the network data is sparse or parallel. At the same time, it unifies the approaches taken on these large scale dynamics and small scale dynamics, so global graph and just a single pair. And then it's a family of random graphs. It connects nicely edge exchangeable graphs and vertex exchangeable graphs for people who are interested in those. And it can be like as personalizable as you like it. So here I would take the kernel parameters to be the same, but they could be different. You could say that the excitation and the kernel part, the hoax part, changes according to the community you're interested in, or according to what time this event occurs or not. And also in the static case, so when it comes to the structural parameters of the actual graph, you can change very easily the assumptions on associativity, for instance, and you can say like the opposite. Actually, the more similar we are, the less the chances that we're connected. So it's very easily adjustable, I would say. And of course, since we're trying to learn why the events happen and what followed what, it can be used as sign, causal learning, and understand, which event caused which event. And yeah, I think this brings me to the end. So thank you very much. I would love to hear your questions and perspectives.